This video is the first in a series of videos that cover the topics in a first semester course of complex analysis. Before we go into the first topic, I wanted to make a couple of comments about complex analysis. And what I mean by that is this will complete your understanding of topics like arithmetic, algebra, and finally calculus. In other words, in the same way that when you start off with a number system, you learn about positive integers, but then you run into trouble because at some point you want to subtract larger numbers from smaller numbers. So you need to expand your set of numbers to include the negative numbers. And also maybe you want to do division, and then you might need to expand your numbers to the set of non-integers, to the fractions. And then, of course, at some point you might want to take the square root of a negative. So I am sure some point in your middle school and high school career, you've learned how to expand the set of numbers to complex numbers. What you are probably missing is you've then learned calculus with real numbers. In this course, we will do a quick review of arithmetic and algebra and complex numbers, and the rest of it will be concerned with calculus, and that is what complex analysis covers. On that note, don't be fooled by our first topics, which are in complex arithmetic and algebra. I know you've seen these before, and they aren't terribly difficult. We have to do that review just for completeness, but we will very quickly get into integration and other complexities, no pun intended, of the complex analysis. But it is true, complex numbers is where some of the most beautiful and elegant theorems lie. And somewhere around the third or fourth video, I will show you Euler's formula, which is considered by many the most elegant formula there is in mathematics. A quick overview of what we will cover in this video. We'll talk about the complex plane and representation of complex numbers in the complex plane. We'll review the rules for summing two complex numbers and taking the product of two complex numbers. We'll look at different ways of representing the complex numbers, and then also we'll go through the algebraic properties of addition and multiplication of complex numbers. There are a couple of other properties we'll look at, and then some identities. And since many of these algebraic properties and arithmetic properties are fairly basic, I will cover them briefly, but I'll also give you a sense of what the proof of, say, for example, these algebraic properties will look like, because you're more likely to get stuck on the proofs than you are the actual arithmetic and algebra. The first thing to know is that imaginary numbers can be represented in the complex plane. So if z is an imaginary number, it's equal to x plus iy, then we can represent it with this ordered pair, x, where x represents the real part of the number, and y, where y represents the imaginary part. An example would be the imaginary number 2 plus 3i. So this 2 represents the x coordinate that is the real portion of our imaginary number, of our complex number, I should say, and this 3 represents the imaginary part of our complex number. So we go up 3 on the y-axis, and we get the point 2, 3. Again, 2, 3 represents the point 2 plus, or the number 2 plus 3i. Another thing to note then, I is represented by 0, since there's no real component, and 1. And I have these few notes over here that x is the real axis here, and then the y-axis represents the imaginary axis. So numbers that lie on the x-axis, so the numbers such as for 0 over here, is purely real. There's no imaginary component. Numbers that lie on the y-axis are purely imaginary, such as this point here, the 0, 1, which represents I. And the other thing that will make complex analysis different from regular calculus is that it takes two coordinates to represent a complex number, whereas when we talked about real numbers, we could just have this one-dimensional line to represent all of our real numbers. Now to represent complex numbers, we need to go into 2 dimensions, and we need a plane. Continuing with our arithmetic, looking at the sum and the product of complex numbers. So this is just like when we have vectors or ordered pairs. If we have a complex number represented by this ordered pair x1, y1, and we want to add it to this complex number represented by x2, y2, we just add component by component. So x1 plus x2, and our second coordinate will be y1 plus y2. An example is if we have the number 2, 3 plus 1, 2, which represents the complex number 2 plus 3i and the 1 plus 2i. So if we go and look at the ordered pairs and add them together, you see that will be 2 plus 1 is 3, and 3 plus 2, which is 5. And that's the same thing we would get when we add these two numbers algebraically, these two complex numbers algebraically. We add the real parts and we get 3, and then we add the imaginary parts and we get 5. So this 3 plus 5i is represented by 3, 5. Similarly, the product is, we want to think of this as then expanding the 2, 3 into 2 plus 3i and the 1, 2 into 1 plus 2i. And now we just use our normal multiplication of two polynomials. 2 times 1 is equal to 2. 2 times 2i is equal to 4i. 3i times 1 is equal to 3i. And then 3i times 2i is equal to minus 6. Then continuing here, our 2 plus 6, adding our real portions together, 2 plus 6 will give us that's minus 4, and adding the imaginary parts together using our sum rule here, 4 plus 3i would give us 7i, so our final answer would be negative 4, 7. For proofs, it is often useful to rewrite our z as x0 plus 0y. So in other words, if z is equal to xy, then we can break this down into x0 plus 0y. And furthermore, using the fact that I is equal to 0, 1, this can be expanded to x0 plus 0, 1, 0y. Next, we have these algebraic properties of complex numbers. First, when you add two complex numbers, you can commute. So z1 plus z2 is equal to z2 plus z1. Also, the multiplication commute. So z1 times z2 is equal to z2 times z1. Addition is associative. So z1 plus z2 plus z3 is equal to z1. You can associate the 2, 3. You can do this addition first. It doesn't matter. Multiplication is also associative. There's the distributive law and the additive identity. I am not going to prove all of these for you, but just so that you get a sense for how they're done, I will do this, that addition is commutative, multiplication is associative, and I'll show you the multiplicative identity. To show addition is commutative, I start with z1 plus z2, and then I'm going to let my z1, I'm going to expand it out as x1 plus I y1, which is equal to in coordinates x1, y1. Similarly, I'm going to let z2 equal to x2 plus I, y2. In coordinates will be x2, y2. So this is what I have here. The next thing I'm going to do then is use my property of how to add two complex numbers. So this is going to be my x1 plus x2 and y1 plus y2. I add coordinate by coordinate. Here now I have two real numbers here, and my y1, y2, these are just the coefficients that go with the I. These are real numbers too. y1 and y2 are real numbers. So I can use the property of the fact that addition is commutative in the real numbers, and I can then switch the order of x1 and x2. So this is equal to x2 plus x1, y2 plus y1. And again, it seems kind of strange because I'm using the commutative property here, which is exactly what I'm trying to prove. But here in my proof, by the time I get down to commuting x1 and x2, and also commuting y1 and y2, I'm talking about real numbers, x1, y1, x2, and y2. They're no longer complex numbers. So I do know that real numbers commute. The addition commutes anyway. And now that I have this form, again, I can just use this, how we add two complex numbers backwards. And so I can have my x2 plus y2, and then my x1 and y1, which is equal to z2 plus z1. Oh, another thing is just a tip. When you do a lot of complex analysis, at some point you start crossing your z's so they don't look like 2, or it's not confusing that it doesn't look like the number 2. Next, I'm going to show associativity of multiplication. And much like the last example, I'm going to, first I'm going to start with z1 times z2. Those get multiplied first, and then z3. And like the last example, I'm going to expand out my z1 to be x1 plus I, y1, which are the coordinates x1, y1. Similarly, for z2, I'm going to expand it out into coordinates x2, y2, and z3 as z3, y3. Now I'm first going to choose this expansion here, where I write out in terms of x1 plus I, y1, and then multiplying by z2, that would be x2 plus I, y2. I'm going to do this multiplication and then multiply by z3. And just like multiplying any normal polynomial, I'm going to multiply my x1 times my x2. I'm going to have an I, x1, y2, and then I'll have my I, x2, y1, and then my minus y1, y2. So I cleaned this up a little bit, and my final answer here is x1, x2, and then I have my I, x1, y2, as well as my I, x2, y1, and then my minus y1, y2. And I have my justification of my step from here to here as multiplication of complex numbers. Oh, and I need to remember that I also need to then multiply by z3. And just a note, if you wanted to multiply my x1, y1, x2, y2, you can do that. You would multiply x1, x2. You just have to remember when you multiply by y, you have to remember to put the I in front. But you would do then x1, I, y2, and then here you would do I, y1, x2, and then I, y1, I, y2. Multiplying this out, so I'm going to start by multiplying x3 by each term here, and I get these first 4 terms. Now I start multiplying I, y3 by each term, so I have I, x1, x2, y3. Here I have my I times I, so I have a minus x1, y2, y3. Here I have again a minus x2, y1, y3, and then here I have my I, y1, y2, y3. Again, that's just by using the rules of multiplication of complex numbers, which I just abbreviated as mult of z. And then I just combined my real portions, which I have 4 real terms, and then I combined my imaginary terms. I should have realized I was going to run out of space because there's so many, all these terms to multiply. But here I just moved up my final answer here to give myself more space now to work on this side of the equation. And here I multiplied everything by my z term. And I'll leave it to you. You can verify that I've done the algebra right. Hopefully I did. And now I can match my terms. So here I have, this matches this, so that's good. It's going to stay just as it is. x1, x2, x3. My next term I have to match is my y1, y2, y3, which I have something similar here. It's in a different order, but it's okay for me to swap the order here, even because we have the fact that our multiplication is commutative. Plus, at this point, we're doing real numbers because the y1, y2, y3, they're just coefficients that get multiplied by I. Now I have my x1, x2, x3. Where is that? y2, y3, so that's this. So I have minus x1, y2, y3. And then last, I have my y2, y1, y3, which is, x2, y1, y3. I'm sorry, I'm just saying it all wrong. Minus x2, y1, y3. And again, it's okay for me to rearrange these terms because we know these are just real numbers and we can commute them. Similarly, if we go through on the imaginary part, we have x1, y2, x3. Where is that? x2, y2, x3. No, that wasn't the right one. It matches with this one. This is an x. x1, y2, y3. Then we have x2, y1, x3, x2, y1, x3. That's here. We have x1, x2, y3, x2, x1, y3, and then last y1, y2, y3. So they match up and they are equal. So in particular, our z1 times z2, z3 with z2 and z3 done first is equal to z1 times z2, z3 with the multiplication. Oops, I did this wrong. So z1, z2, z3 with z2, z3 multiplied first is equal to z1, z2 times z3 with z1, z2 multiplied first. So this here is equal to this. So it shows that these two are equal. The last thing I'm going to show is that 1 is the multiplicative identity. So I'll let z equal to x1 plus I, y1. Actually, I didn't even have to put the 1s. I could have just said x plus y. And I will let 1 equal to 1 plus I times 0. So there's no complex portion of 1. And I'm going to see what z times 1 is equal to. So I have my x plus iy times 1 plus I0. So multiplying out, I have x times 1 gives me x times I times 0 is 0. Then I have my iy times 1, which is iy, and my iy times I0 is 0. So I am back to my original z. Technically, for this multiplicative identity, I also need to show that 1 times z is equal to z. But since 1 times z is equal to z times 1, because multiplication of complex number is commutative, I have that this is also equal to z. And just one last warning, 1, 1 is not the multiplicative identity, because if we have x plus iy, some random complex numbers, times 1, 1, and 1, 1 would be 1 plus I. When we multiply this out, we get x, which is great, but then we have this xi, which is an extra term, so already we're in trouble, and then of course we have the iy, which is great, but then we have this minus 1, which is another extra term, so it's not equal to x plus iy. So the multiplicative identity is 1, 0. Take a look at the other properties, give a try proving them, make sure you have the correct additive identity in the same way you wanted to make sure you had the correct multiplicative identity. Next, we have how to find the multiplicative inverse. So if we want xy, if the inverse is equal to uv, we want it to equal to 1. And again, it's not 1, 1, it's not 1 plus I, we want 1. I'll do the work here to show that the inverse then is equal to x over x squared plus y squared and minus y over x squared plus y squared. But I'm going to clear some things out so I have more room and don't run out of space like my last example. So I've moved up the information. I want xy times uv, and if uv is the inverse of xy, that should give me 1. So I've expanded out xy as x plus iy and uv as u plus iv. I multiply, I get xu, I get I xv, I yu, what's that right? I yu, and then minus yv, and that should equal to 1. Expanded out, that would be 1, 0. Now I'm probably going to group this together, so I have xu minus yv is equal to 1, and then I have my xv plus yu is equal to 0. From here, I can group my real parts together, my xu and my minus yv, and set that equal to 1. And then I can group my imaginary parts, xv and yu, and set that equal to 0. And at this point, we have two equations. My xu minus yv equals 1, and xv minus yu is equal to 0. So we have two equations and two unknowns. Remember, we know what x and y are. We're trying to find u and v that will give us our inverse. I have my two equations, so I take this bottom equation and I solve for u in terms of v and x and y, which are given. We know what those are. And then I plug my u in to this equation here, so I have x times u minus y times v is equal to 1. I solve, and I get v is equal to minus y over x squared plus y squared. Similarly, we can do a calculation to show that u is equal to x over x squared plus y squared, and hence we have found what our inverse of z is equal to. X over x squared plus y squared minus y over x squared plus y squared. We have finished looking at the algebraic properties and finding the multiplicative inverse. So the next statement we want to look at is if a product z1 times z2 is 0, then so is at least one of the factors z1 and z2. A corollary, if two complex numbers are non-zero, then so is their product. Looking at this top statement here, so it says if a product z1, z2 is 0, then so is at least one of their factors, z1 and z2. So I rewrote this, so z1, z2 equals 0, then either z1 is equal to 0 or z2 is equal to 0, or both, but we're going to say at least one of these is true. There is this really nice proof technique that I always feel very clever whenever I use it. Whenever you are trying to prove that either one result is true or another result is true, what you can do is break this up into cases where the first case you assume the first result is true, and then you are done because you've proven the OR statement by proving the first part of the OR statement is true. And the second case is you assume that your first statement is false. And then from here, you go and show that it is necessarily true, that the second statement then must be true. But again, this is the idea. If you have two things that you want to prove an OR, you can break this up into cases where you say the first case is true, and the second case, the first case is false. And you can see how this is going to work out. Either z1 is equal to 0, and we're done with our proof, or we say z1 is not equal to 0. Well, we're given that z1, z2 is equal to 0. That was given, so I'm trying to write my justification for my proof steps on the right. And then we know that we can multiply both sides of our equation by z1 inverse, which we had just talked about how to find. So I'm going to multiply both sides of the equation by z1 inverse, and we know that it exists because of our properties of complex numbers. And now I combined two steps. I both kind of rearranged my terms on this side. So because multiplication of complex numbers is commutative, I can do that. And then second, I decided to do the z1 times z1 inverse first. And I can do that because multiplication of complex numbers is associative. On this side of the equation, I have 0 times any vector will give me 0. It's the 0 vector after all. Here, by definition of z inverse, z1 times z1 inverse is equal to 1 times, and now we have z2 equals 0. And then finally, by definition of the multiplicative identity, which 1 is, we have z2 is equal to 0. So we have proven that if z1 is not equal to 0, it must be the case that z2 is equal to 0. So you can see how this falls out nicely. And again, it's a nice way of introducing a proof where if you have to prove an OR, you can assume the first part is true, and your second case is the first part is false, which leads to the second part being true. This next statement about division, so dividing complex numbers, is the same thing as multiplying by the inverse. And since we have defined what this inverse looks like, I can take a closer look at that. I'm going to let z1 equal to x1 plus I y1 and z2 equal x2 plus I y2, and I have the definition of the inverse of z for your reference here. Now I can write z1 over z2 is equal to x1 plus I y1, that's my z1, over z2, x2 plus I y2. And then for comparison, I'm going to compare that to z1 times z2 inverse, and I plug in my definition of z2 inverse over here. So it's x2 over x2 squared plus y2 squared minus I y2, x2 squared plus y2 squared. And now I can do that lovely multiplication. So I have my x1 times x2 over x2 squared y2 squared. I have I y1 times I y2, which will give me a minus, where did I write that? A minus, oh, except there's another minus here, so I get a plus y1, y2 over x2 plus y2 squared. And then I have my x, what do I have next? Oh, and then I have my x times my, let me do this in green, times my I y2, which is over here. And then finally, I have my I y1 times x2 over x2 squared plus y2 squared. I didn't want to do a lot of algebraic manipulation of this to show it's equal to that, but what I did do then is I took my z1 over z2 and I multiplied by its complex conjugate, which we hadn't defined yet, but for now I'm just going to say it's x2 minus iy2 over x2 minus iy2. So you'll see this is really just equal to 1. So I can do this. And basically what I did is I multiplied it by the denominator with the minus sign. I just changed the sign of what's between the real and the imaginary part. So when I do this multiplication, and you can do out the algebra, you'll see that you get exactly what we have written here. And so this is how we can show that z1 over z2 is equal to z1, z2 inverse. And just a quick example of division, just because I guess everything's been pretty much symbolic. So 1 over 2 minus 3i times 1 over 1 plus I will give me 1 over 2 minus 3i, 1 plus I, and now I do my multiplication. 2 times 1 gives me 2, 2 times I gives me 2i, minus 3i times 1 gives me minus 3i, and minus 3i times minus I gives me positive 3, which is equal to 1 over 5 minus I. And just because sometimes people don't like to leave the I on the denominator, we can multiply my 1 minus 5i by its complex conjugate on top and bottom, so just it's equal to 1. But again, the complex conjugate is the same complex number, except you switch the sign that separates the real from the imaginary parts. And then you'll have my 5i plus 1 over multiplying this out, 25 plus 5i minus 5i, so those cancel out, minus I squared, which is just plus 1. So I have 5 plus I over 26. I can separate this out, two fractions, 5 over 26, and then I times 1 over 26. So my coordinate, my representation as an ordered pair of this complex number would be 5 over 26, 1 over 26. Now we are getting to the end of our topics. So we have a couple of more identities, and as well as the fact that the binomial formula remains valid with complex numbers. And here is the binomial formula. It tells you how to expand a number plus another number raised to the nth power. And this is the formula in case you haven't seen it in a while. For these identities here, and technically I should prove that this is equal to this, which is equal to 1. I am just going to prove this top one and only this first part of the equality, that this is equal to 1. And I'll leave the rest as exercises for you, but they more or less follow the same sort of idea. So I start with z1, z2 times z1 inverse, z2 inverse is equal to, well, I can switch the order of these two because I'll tell you the game plan. What I want is I want to get the z2 next to the inverse, because that will just give me 1. Well, I can switch the order of these two factors because multiplication, that's what this x is, multiplication is commutative. And then I can associate these two. I can do the multiplication of the z2 times z2 inverse first because multiplication is associative. Well, this here is equal to 1 by definition of the inverse here. And then this is equal to z1 times z1 inverse because 1 multiplied by anything just gives you what the anything was, and that's because 1 is the multiplicative identity. And then finally, z1 times z1 inverse is equal to 1 by definition of inverse. Next, we'll look at the binomial formula, which lets us expand two complex numbers, z1 plus z2 added together to the nth power. And we've seen this with real numbers. So with real numbers, we usually just call them real number x and real number y, and we'd have that raised to the n, and then we would do this binomial expansion, and we can use this formula to do that. So it'll basically tell us what the coefficients in front of each term is. That's what this binomial expansion formula does for us. And the formula says it's a summation from k equals 0 to n, and choose k, which is defined here as n factorial k factorial over n minus k factorial. That's also the number of ways to choose k items from a list of n items. Anyway, times z1, our first complex number raised to the n minus k, plus times z2, our second complex number raised to the k. I am not going to prove this for you because that's way beyond this class, the scope of this class. I mean, it's not difficult, but it's not what we're doing. But I will show you an example of how to use it. So let's say you have z1, z2, and you want to raise it to the fifth power. In this case, n is equal to 5. So plugging in n equals 5 into this formula here, we're going to get k equals 0 to 5, and choose k, which is 5 factorial over k factorial, 5 minus k factorial, z to the 5 minus k, and z2 to the k. Now we just need to do the summation. So we start with k equals 0, so we get 5 over 0 factorial, 5 minus 0 is just 5 factorial, z1 is to the fifth, and z2 to the 0, which is just equal to 1. Now we plug in k equals 1, so we get 5 over 1 factorial, 5 minus 1, which is 4 factorial, z to the fourth, z2 to the 1. We plug in k equals 2, k equals 3, k equals 4, and k equals 5, and then simplifying algebraically, which, by the way, there's an easy way to simplify some of these factorials. For example, if you have 5 factorial over 3 factorial, 2 factorial, that's equal to 5 times 4 times 3 factorial. I don't write this out any further because I can cancel right away with this 3 factorial. So I'm left with 5 times 4 divided by 2, which is just 10. And here how is what it simplifies down to. This is the expansion, my binomial expansion, which is called the binomial formula of my z1 plus z2 to the fifth. To review what we have covered in this video, we looked at the arithmetic and algebra of complex numbers. First, we defined the complex plane. We said that a complex number can be represented by an ordered pair, where the first of the ordered pair is the real part of the complex number, and the second number of the ordered pair is the imaginary part. It's the part that gets multiplied by I. And then we can graph that in 2 dimensions, just as we would any ordered pair on the xy plane, where x stands for the real numbers and the y-axis is the imaginary part. We defined how to add 2 complex numbers, and it's just like adding 2 ordered pairs. We defined the product, which for this product, it's equal to this ordered pair here. And the best way, I feel like the best way to develop this ordered pair is by writing this out as x plus iy, 1 times x2 plus I y2, doing the expansion, the multiplication, and then figuring out what the first coordinate would be of the product and what the second coordinate would be for the product. We talked about how in the future, and also for proofs, it might be convenient to write z to separate out the real and the imaginary component, and also to remember that 0, 1 is considered to be I, because this is no real component and 1 in the on the imaginary axis. We went over the algebraic properties of the complex numbers. They are commutative, addition is commutative, multiplication is commutative, addition and multiplication are associative. We have this distributive law, and we have the additive identity is 0, the multiplicative identity is 1, and then we talked about finding the inverse, and we have this formula given as z inverse is given by our formula x over x squared plus y squared, and minus y squared over y squared plus x squared plus y squared. Sorry, I said that wrong, but you can read it. There it is. And then we also talked about this corollary. So if the product of 2 complex numbers is 0, so then at least one of the factors, z1 or z2, is also 0. And the corollary of 2 complex numbers are non-zero, then so is their product. We talked about division and how you can think of division. You can actually divide or you can multiply by the inverse. We have these other identities where it's just different multiplication with the inverses. And then we also looked at the binomial formula, which allows us to do this binomial expansion of the sum of two complex numbers, and we did an example of that. On this slide, I have two problems for you to try. I suggest you pause the video, give the problems a try, and then come back, and I will have some solutions for you. Here are the solutions. So that's it for this video. Thank you for watching.